Hello and welcome. Today we're going to be having a lecture on a very kind of like difficult integral. But the way we're going to do that is with gamma function. So you need to have a look at all your basics on the gamma function. So this is not standard A level, is kind of university maths, but very simple stuff. Is the gamma function. So we need to know the definition of the gamma function. I will write it when it appears within the working. So for something like this, first of all, the gamma function has limits 0 to infinity. So we're going to start with a substitution, which motivates us perhaps to try something. And I'm going to say, okay, let's use a substitution. U is minus the log of x. We want a minus in front of the log, and you will see from the limits why. It's because we'll reverse the 0 limit to plus infinity eventually. So let's do all our bits here. So first of all, du by dx. This is not a straightforward gamma kind of like application. This is one of the more involved ones now. So it's going to be minus 1 over x. So clearly my dx is going to be minus x du. And maybe we should really write this a little bit different as well. The dx, I don't know if we need it like that, but since we have a log in there, let's write, I should have written straight away in the beginning. In this particular case, minus u is equal to the log of x. So if you e both sides of the equation, e to the minus u is equal to x. So we could have actually differentiated from there. So our dx is in fact a minus x as minus e to the minus u du. So that's that or that. So I have a few results basically ready for that. And let's have a look at the limits, because I mentioned why I put this minus at the front. When x is equal to 0, so we can look at this particular case. Now, the log of 0 is minus infinity, but with a minus at the front, it will map now to plus infinity. And that's why I put the minus. And when x is equal to 1, the top limit there, then u will map the log of 1 is 0, so the minus makes no difference. It will go to 0. So let's start transforming this integral. So we got the 0 goes to infinity, the 1 goes to 0, so we have the limits that we desire, but they're the wrong way round. In the x log x, I'm going to write this as e to the minus u. I'm using this x here. The log of x is, of course, a minus u. The log of x is a minus u, so we can write that at the front. Let's write it in bits so we don't make a mistake. To the power of n. The dx, of course, a minus e to the minus u du. And this is from differentiation, the dx minus e to the minus u du. So hopefully I haven't missed anything. So the first thing we're going to do is we're going to lose this minus and reverse the limits, 0 to infinity. And then we're going to have, again, let's take it in steps. I'm notorious for mistakes. So nu, and then this minus now will still be in there, minus u. Careful, we cannot lose this minus to the end, so we don't know if it's plus or minus. I forgot to mention, and there is a positive integer in the integral. So I do apologize. You're not to assume that unless you're being told, of course, and I'm telling you now, it'll be late, I guess. So my apologies. And that, of course, is the e to the minus u, and this minus is the one that I use to flip the limits, du. Okay, I can continue from there, not to infinity. Next step, I guess this minus is annoying me, so I'm going to pull it outside the integral. So minus 1 to the power of n. That's the minus from here. And perhaps at the same time, I can put the two exponentials together. So this will give me e. We got nu and u, both with minus. Put the minus outside. Factorize the u. Let me write it because my excuse is, I've seen some might make a mistake. The fact of the matter is I'll probably make a mistake. So that e to the minus u. And then, of course, the minus I wrote at the front, so that's going to be a u to the n du. And now if you look at minus nu, minus u is equal to a minus u n plus 1. So that's the exponent of that. So far, we have this quantity here, e to the minus u n plus 1. And then we go u to the power of n du. That looks like a gamma function, with the exception of this bit here. So we just need to have a single variable. So here it should be a minus u, a minus t, a minus x, not all of this mess. So we need another substitution. So because we're not going back into our substitutions, I hope I haven't made any mistakes. I'm going to wrap this off. And the substitutions, again, is a simple linear substitution. Call this a single letter. So let t equal to u n plus 1. I need the minus to be a minus t there. So dt is equal to n plus 1 du. And what do we want? Du is 1 over n plus 1 dt. So this is the substitution and the limits. When we got 0 and infinity, that's in u's in this integral. So what happens there? When we put in u is equal to 0 in there, t will be 0. When this is infinite, this is a positive integer, t will be infinite. So the limits are in fact unchanged. So this will give us minus 1 to the n outside the integral, unchanged limits, e to the minus t, and then the u, now that's going to be a little bit of a nightmare. We need to kind of rearrange it a little bit here in order to put the u in there. U is t over n plus 1. So it's going to be t over n plus 1 all to the power of n. D, and we have, of course, the du, and the du is 1 over n plus 1 dt. Okay, we're going to do a couple of things at once. So we don't run out of space. So minus 1 to the power of n. Thinks that this is the integral with respect to t. So this n plus 1's here and here can be factored out. So I'm going to have 1 over n plus 1 to the n. That's from this one. But of course I got another spare one from there. So I'm going to write it n plus 1 straight away. And then I still have the integral 0 to infinity e to the minus t. And then of course we have what we got left there. We got t to the n dt. And then of course we need the definition of the gamma function, which is as follows. The gamma of x is the integral from 0 to infinity e to the minus, I use t there, it doesn't really matter, e to the minus t, and then we got t to the x minus 1, and of course in order to have with a function of x, this needs to be dt. So if we look at the result here, e to the minus t, t to the n there, so our integral here is in fact a gamma function, and a gamma function is going to be minus 1 let's actually write a little more compactly to save space. -1 to the n, that bit there, n plus 1 to the power of n plus 1, that bit there. And this is, of course, the gamma of n plus 1 by definition. Okay, so if this is one more than what we got in there. And of course, if n is a positive integer that I didn't write down, but I did mention it, this is, of course, n factorial. And therefore, we have a final answer, -1 to the n times n factorial. Actually, it's so beautiful. I really want to write in a different color pen. So let's have a look what colors we have available. We have a red color, so that's all good. So that's -1 to the power of n factorial divided by n plus 1 to the power of n plus 1. So no matter what power we have there for the n, as long as a positive integer power, all we need to do is just plug in the values of n in this quantity and we'll have the exact value of this integral. I hope you enjoyed it and I hope you liked it. This was quite a more involved integral using the gamma function. I'm going to be signing out and I'll see you real soon. Bye for now.